Alright, what's up? So as you can see, I've already written a few things up on the board. That's because my camera is about to die, so let's just get into this lecture. This one's going to talk about some vastly different things. We're going to talk about power, and then we're going to talk about a fourth type of energy, internal energy, which is going to be the last type of energy. We will talk about this entire unit. So yeah, let's just get started. Power. Power is defined as work over time, right? Power, this is the definition of power, how much work you can do in a certain amount of time. And this is also, if we write it in like differential form, this is dw over dt. So if they give you w is equal to like 2t squared, well, we can differentiate with respect to t to figure out what power is, and we get like 4t or something. But what I think is more important for the AP exam is that we also know that power is, right, work is force times distance, and then we still have this over t, which is equal to F times x over t, right? I just rearranged it. Well, x over t is velocity, right? So this is force times velocity. That's something else very important to know. I have seen AP questions, they'll give you v, or they'll force you to solve for v and f, but they won't tell you what t is, they won't tell you what x is. So you virtually can't use this equation unless you do some very, very difficult things. So it's best just to remember F times V is also equal to power. How can we justify this other than this? Well, let's look at the units. Power is in something called watts, which is unfortunately represented with W just like work. Well, a watt is a work per time, right? So the unit for work is joules per second. Second is in time, right? Well, a joule, if you remember, is a Newton meter. Newton meters per second. And that's just a Newton times a meter per second, right? A Newton is our unit for force, and a meter per second, well, that's our unit for velocity, right? There we have it. This is pretty much all you need for power. Yeah. Awesome. So now, yeah, so power's in watts, that's how you spell it. Okay, yeah, now let's just get into the second thing I want to talk about, which is internal energy. So before I give the lecture, right, grab your hands, right, and rub them together. Do you feel like warmth being generated in your hand? That's a rise in internal energy, right? It's getting warmer, you can feel heat because it's created by friction. Resistive forces like friction are going to create heat. So all the work that's done by friction is going to be something we call internal energy. So like we learned about three types of energy already, right? We got gravitational potential, we got what's this called? Kinetic, yeah, right? Kinetic energy. And we got spring potential. But now, we got this new thing called internal energy. Or, some people also call it E-thermal. You can also write it as internal energy, or like E-internal. It's all good. These are all the same names for the same concept. Which is just like, it's not necessarily heat, but for the physics test, right? We can just think of it as like the temperature is increasing, things like that. Not the formal definition I know, but for physics we can just think heat is increasing because friction is doing work. So, let's say friction, we had a frictional force that was like 10 newtons, and it was acting on us for 10 meters, right? And then we wanted to calculate the change in internal energy. Well, friction did work, right? Friction did how much work? 10 times 10 newtons times 10 meters work, so that's 100 joules of work, right? So we would say we had an increase of 100 joules of internal energy. Okay, so now, let's just do a practice problem. You've learned pretty much all that's needed for this unit, but I think it's good to tie in this unit and the force unit so we can see, practice one last time how all these concepts can tie together. Yeah, so this is a problem that my physics teacher gave me, and I'm going to be honest, it was really hard. Like, I had to go back to the solution guide a couple times when I was studying for this, but okay, basically, they give us a ramp, right? This is a ramp perpendicular to the ground. I know, I drew it bad. Okay, and then we got a box. The box is 5 kilograms, right? And then, in 2 seconds, right, the box slid down 2 meters. Now, the question is, how much net work was done? Like, net work done in the system, right? Okay. Well, network. We haven't heard network before, but we can piece together some clues to figure out what it means. We know net force, right? We can calculate the net force by using the free body diagram on this box, right? The only forces acting throughout the entire thing are going to be gravity, right? The weight. We got the normal force, which is perpendicular to the surface. And then we also got friction that's acting against it, right? A frictional force. So net work is just going to be the work done by all of these forces. Okay, so that's fine and all, but how exactly do we go about calculating? Let's start with the easiest one, F of n, right? So we know the equation for work, right? Work is equal to force times distance times the cosine of the angle between them. Remember, cosine of 90 degrees is 0, right? And we also know our normal force is perpendicular to the surface, right? Here is our normal force. So 5 kilograms, I was pointing to the box. Our normal force is going to point up like this way, right? Our surface points this way, right? This is perpendicular. If they're perpendicular, the angle between them is 0, which means no work is done, right? So I'll say there's 0 joules of work done by our normal force. Normal force bad. Okay, now let's go with the force done by weight. Okay, so what we can do is we can just take, find how much force is, weight is, right? Well, Fw is equal to mg, right? So I'm just going to say m, which is 5 kilograms, right? 5 kilograms times g, which is 10 meters per second squared. But on the AP exam, they'll probably make you use 9.8 meters per second squared because the actual approximation is like 9.801 or something meters per second squared. Yeah, so if you're doing science bowl stuff like that, 10 is fine. Maybe they'll actually calculate 10. But on the physics exam, right, you're allowed a calculator, so you want to make sure you get, you plug in 9.8. All right. Then we got to multiply by x, the distance traveled. Well, 2 meters, easy. Right? But then here comes the hard part, cosine theta. Well, we know weight acts straight down, right? Okay, so if this is straight down, this means it makes a right angle with this table. We know this is 30, 90, so that means this has to be 60 degrees. So cosine 60 degrees is 1/2. We multiply all of these together, and what do we get? Well, we get 50 joules. I'll leave it as an exercise to the reader to figure out why the units turn into joules. Okay, yeah, so we've gotten 2 out of the 3. Unfortunately, friction is a bit difficult, right? I said we're going to have to use our concepts with force. So, with friction, all we have to do, right, is we know the angle between, let me see, here. So, we want to find F times distance traveled, which is 2 meters, right? We know because the box moved 2 meters, multiplied by cosine theta. Well, friction always opposes action, right? So F is this way, so it's going to be 180 degrees, right? We turn our marker 180 degrees. So, cosine of 180 degrees, that's -1. We're so close to finding what work is, but now we just have to figure out what the frictional force is. Okay, then let's go ahead and do that. What we have to do is we have to know, right, what are the only forces acting in the horizontal direction, the only forces that would push the box this way? Well, the only forces that are pushing the box this way are this one component of weight, right? This component of weight that's this way, which we said in a previous video is just going to be sine of this angle multiplied by weight, right? So I'm going to write our net force in this direction, right? Net force in this direction is equal to our frictional force plus this gravitational force in this component, which is Fw sine 30 degrees. Well, sine 30 is just equal to 1/2. So, and we know Fw is mg, so that's like 25, right? M times g, right? Mass times gravity, that's 50 times 1/2, so we get 25. So it's equal to F plus 25, 25 what? 25 newtons, because we have, we're talking about forces here, not work anymore, right? These are forces. And we know this is the net force. Well, we also know net force is equal to mass times acceleration. Okay? If net force is equal to mass times acceleration, that means we just got to find what the acceleration is, right? We know the mass, 5 kilograms. Well, can we find the acceleration? Yeah, of course we can find the acceleration, right? What we can do is we know that our acceleration is constant, right? F and Fw don't change. So what that means is our acceleration, right? Or sorry, our displacement is equal to 1/2 at squared. We know 2 seconds passed. And we know how much distance we traveled, 2 meters, is equal to 1/2 a times 2 seconds squared, right? So on this side I get 2 meters, on this side I get 2 seconds times acceleration, so I get acceleration, or second squared, so 2 seconds squared, right? So if I divide both sides by 2 seconds squared, I get acceleration is 1 meter per second squared. Okay? MA, right, would be 5 kilograms times 1 meter per second squared. That makes it 5 newtons. Alright? So we got 5 newtons is our M times our A. Okay? So now we move the 20 over to this side, and what do we get? We get F, right? F is equal to negative 20 newtons. We solved for F, right? All we had to do is we just had to remember net force is equal to this stuff, and then we had to plug in our kinematics. Look, we're tying everything together. And then, right, then we can finally plug it into here, and then we can get is equal to negative 20 times 2 times negative 1, right? So our work done, I messed up. This should be a negative F, sorry. Yeah, so it's positive 20, right? It's negative F because F is in the opposite direction of FW sine theta, right? So we had, sorry. I gotta make sure, you have to make sure that you keep track of everything that's, all the different directions, right? Because, let me explain, right? Force would be traveling, the weight would be pushing this way. Our friction is going this way. Our net force, we don't add the magnitudes of them together, right? If we added the magnitudes together, it'd be like friction was pushing the box forward more. No. We have to put a negative here to indicate that friction is actually hindering the this force, right? It is counteracting this force, so that's why we got to put a negative here. So then when we solve, we get friction is positive 20 newtons. So our work would be negative 40 joules, right? If the question had just asked calculate the change in internal energy, well, it'd just be 40 joules, right? Because friction did negative 40 joules of work. Right? It opposed our work by negative 40 joules, which means that energy had to go somewhere. It was pulled out of the kinetic energy of the system. It was pulled out of the potential energy of the system. So it had to go somewhere, right? Conservation of energy, and the only other energy, right? We list all the energies, US, and then E thermal, right? All the energies. This one's decreasing, right? This one's decreasing. It's taking out of this one, it's taking out of this one, it has to be raising this one, right? Any work done by friction is always going to be, raise our internal energy. Okay, so what we can do now is we can finally say this is negative 40 joules. Right, we want to find the net work, we add all of these together, we get 10 joules. Our net work is 10 joules. That was a long and complicated process, and I definitely recommend you do this problem yourself, right? Just take your ramp of 30 degrees, just know 5 kilograms, 2 meters, 2 seconds, and try to see if you can derive the same thing. Right? It's one thing seeing it, but deriving it is like something else. It's really forces you to think about all the things you've learned before, and think about applying all the different things that you've learned before. Yeah, so with that, I'm going to do one last thing, right? One last thing, and that's just to consider what all the work looks like. All right, so 10 joules of net work was done to the system, but what if I consider the sum of all the energies? This is a different concept. Right, so internal energy, right? So we already said the work done, we can calculate our change in gravitational potential energy, right? Remember, this is separate from the work done by weight. This is our change in gravitational potential energy, right? Our weight is not only pushing it down, right? So it's decreasing our gravitational potential, but it is also pushing the box forward. It is accelerating the box. So this weight is actually affecting both of these, right? We want to make sure that we keep these things distinct, right? This is the work done by force or by weight. This is the change in gravitational potential energy. So now we're going to calculate this. All right. So to calculate this, right, all we have to do is realize, right, so this is sine theta by some trigonometry. So we just have to do sine theta, 2 times sine theta, so that's 1, right? We changed a height of 1, right? So m, which is 5 kilograms, g is 10 meters per second squared, and then h, which is 1 meter. And what do we get? We get 50 joules of work, or 50 joules that change in gravitational potential. Did we gain or did we lose, though? Well, our box is moving down. That means we lost energy, right? We lost potential energy. It has less ability to do work now that it's lower, so we got to make sure we got that negative sign there to indicate we actually lost work. We can also show that we got negative energy because we moved -1 meters. Next, our kinetic energy, that's 1/2 mv squared. Can we calculate V? Yeah, of course! We know what A is. We know it's a kinematic system. So we know V is equal to just A times T, which is equal 2 seconds times 1 meter per second, which is equal to 2 meters per second. Right? So here, right, we want 1/2 mv squared, which is equal to 1/2, right? 1/2 multiplied by m, which is 5 kilograms, multiplied by our V, which is 2 meters per second, right? And we got to square it, and what do we get? We get 10 joules, right? 10 joules of kinetic energy. Remember, there's no spring in the system, but remember how I said all work done by friction is always going to raise the internal energy. Even though friction did -40 joules of work in accelerating the box, in pushing the box this way, what it did do, where its work went, where these -40 joules went, was it went out of accelerating the system, but instead it created heat. So when the box is sliding, it becomes hotter and hotter. So we get 40 joules, right? The opposite sign of what that was of internal energy. Now watch this. Law of conservation of energy says that we're going to start with the same amount of energy as we ended with, right? If I said we started with 0 energy right here, this is the energy changes that would have occurred. And if we sum all of them, -50 plus 10 plus 40, we get 0 joules of energy change. There's no difference than the amount of energy we had before, right? These are all the energy changes we saw. No change in energy. Law of conservation of energy works. Yeah, with that, end of this unit. Good luck studying, have fun. Yay, AP test is going to be a grind.